Welcome back, folks. Last time we talked a little bit about diffusion and the movement of solids down concentration gradients and down electrochemical gradients. And I just want to reintroduce the principle about diffusion, which often gets missed, that when diffusion occurs, it's going to move towards equilibrium. And we'll follow that by looking at some quantitative kinetics in regard to the rate of diffusion in terms of simple diffusion compared to facilitated diffusion. So diffusion will always tend to create a uniform solution in which the concentration is the same everywhere. Solids will move toward a region of lower concentration from a region of higher concentration until the concentrations are equal. And so that's a long-winded way of saying that diffusion is always movement towards equilibrium, towards the lowest possible free energy state of the system. And as you know, lipid bilayers are more permeable to non-polar substances than they are to polar ones. And so non-polar substances will dissolve readily into the hydrophobic region of the bilayer, and large non-polar molecules, even things like estrogen and testosterone, will move across the membrane easily despite their large size. So when we get to the point of thinking about simple diffusion versus facilitated diffusion, we'll be looking at different characteristics of solutes as determining whether simple diffusion or facilitated diffusion can work. So a lot of this diffusion being dependent on the characteristics of the solute comes back to the polarity of the solute. And so the polarity of a solute can be measured by its ratio in an organic solvent to its solubility in water. And that gives us a value called the partition coefficient. Now, in general, the more nonpolar or hydrophobic a substance is, the higher its partition coefficient will be, and that gives you an indication that it's more hydrophobic, obviously, and it will move freely through the hydrophobic core of the membrane. Diffusion, like all chemical reactions and physical processes, proceed in the direction of decreasing free energy, and diffusion is the same as I mentioned. Free energy is minimized as the molecules move down their concentration gradients, and so at thermodynamic equilibrium, where solute concentrations are equal on either side of a membrane, there's going to be no further net movement, and the standard free energy of the system has reached a minimum point. There will be no more diffusion. So let's kind of put this in biological context. Possibly this has been best studied in red blood cells, and we can bring in some transport proteins in the red blood cells as well. So there are two things that is going on in the red blood cell. There's simple diffusion down a concentration gradient, there is some facilitated diffusion, and there is an electrochemical gradient. So the membrane potential that affects the electrochemical gradient in terms of the movement of charged solutes, and here we'll be looking at chloride ions and bicarbonate ions, that membrane potential is maintained by the active transport of potassium out of the cell and sodium in. So if you think back to the sodium-potassium transporter, we're going to move 3 potassium out for every 2 sodium that comes in. That's going to give us a net negative charge on the inside, and that's going to influence the movement of solutes which are charged because of the establishment of a membrane potential. So as well as simple diffusion of carbon dioxide and oxygen across the red blood cell membrane, and facilitated diffusion using the bicarbonate chlorine anion exchanger, there's also going to be movement of water in now as well, and we don't worry about the water too much because it's not really affected by a gradient, because the situation is maintained at isotonic balance internally compared to externally across the cell membrane of the red blood cell. So that's kind of the situation. So is what's happening in a red blood cell. Let's start at the top here. If we're in tissues, so the blood is circulating through tissues where oxygen tensions tend to be lower because the cells are using oxygen as an electron acceptor for cellular respiration, that depletes the oxygen levels, and cellular respiration elevates the carbon dioxide levels. So in this situation, carbon dioxide is diffusing down a concentration gradient into the cell. So the concentration of carbon dioxide is low in the cell. Carbon dioxide diffuses in, oxygen diffuses out, and we'll talk about how oxygen is released from the red blood cell hemoglobin a little bit later when we talk about something called the chloride shift. The carbon dioxide that comes into the red blood cell combines with water, and that reaction is catalyzed by an enzyme called carbonic anhydrase. That produces protons and bicarbonate, and the bicarbonate is transported out of the cell into the blood plasma, and concomitant with that movement out, chlorine is moved in. So this is maintaining the charge balance across the membrane. And so most of the carbon dioxide in blood is transported outside the red blood cells in the form of bicarbonate. And so then if we go down to looking at what's happening in the lungs, where we have high oxygen levels and low carbon dioxide, we effectively see a reversal of the system. Bicarbonate is brought into the cells and chlorine is moved out of the cells. The bicarbonate then associates with a proton, is catalyzed by carbonic hydrase working in the reverse direction compared to up here in the tissues, and that produces carbon dioxide and water, and the carbon dioxide is then released from the red blood cells and can be exhaled in the lungs, and oxygen diffuses down the gradient into the red blood cell to bind with hemoglobin, and then the process is reversed if the red blood cells end up traveling back through the body, through the general circulation into tissues. So you can see here, even in a simple system like a red blood cell, we've got a lot of transport going on using lots of different mechanisms. So hopefully this helps you see that multiple things are happening to maintain the homeostasis that's required so that we can have efficient gas exchange. Let's just finish up by taking a look at some thermodynamics of diffusion and comparing simple diffusion with facilitated diffusion. So thermodynamically, simple diffusion is always an exergonic process. It requires no input of energy. If something can diffuse down a gradient, there'll be a release of free energy, and delta G will be negative. And until we reach equilibrium, obviously, and then there is no change in free energy and the system can do no more work. So in that system, kinetically, the rate of diffusion, simple diffusion, is directly proportional to the concentration, the solute concentration difference across the membrane, so the size of the gradient. So as the gradient size increases, as we have more solute outside compared to inside, for example, as we increase the difference between these two values, we see a greater rate of diffusion. And so the movement inward is equal to this constant P, which is the permeability coefficient, and that's a variable which depends on the thickness and the viscosity of the membrane. Obviously those are affected by membrane lipid composition that we talked about last time, multiplied by the difference in the substrate concentration inside and outside, and that's just the gradient. And so you can see is that this rate increases as a function of the difference in the size of the gradient. The bigger the gradient, the faster the rate of diffusion. Now let's compare that to what happens in facilitated diffusion. Now facilitated diffusion, we have this initial rate here where we see that the rate is again directly proportional to the solute concentration, but then or the solute difference across the membrane. As we start to increase the magnitude of the gradient, we see that the rate starts to drop off, and so at some point over here off of the graph, this rate will effectively flatten, and we can't really get a much higher rate of diffusion in terms of the velocity of the movement of solutes. And so you can think about that value as kind of as Vmax, if you like. So what's happening here is that down here, if we think about a channel, the channel's open and it's allowing solutes to pass, and more solutes can pass as a function of an increase in the size of the gradient. But at this point, it doesn't matter how big the gradient is we can't get any more of the solutes through the channel, because the channel only has a particular diameter, and so we can't get more solutes through. They're usually going through one at a time in a column. If that were a transporter, then bear in mind the transporter is going to grab a solute on one side of the membrane, change shape and flip it through, and there's only so much so you can only go back and forth between the two states at a certain rate, and so once we hit that rate limiting step, it doesn't matter how much more you increase the concentration gradient, you don't get a faster rate. And so the kinetics for a solute being moved by facilitated diffusion is different from a solute just moving by simple diffusion. These rates will initially be much faster for facilitated diffusion, but then they will slow down. Simple diffusion is often going to be slower, and like we say, it's directly proportional to the size of the concentration gradient. So that's it. We'll finish up there, and I'll be back soon.